Tonight, we're going to take a journey to one of the most fascinating worlds in our solar system, Pluto, a tiny frozen world at the edge of our solar system that represents both the limits of what we've achieved and the vast distances that still separate us from the cosmos. We're going to answer a deceptively simple question. How long would it really take us to get there? And by the end of tonight, you're going to understand why the answer reveals something profound about space travel, about the scale of our solar system, and about the immense challenges we face when we try to leave our home planet behind. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When most people think about Pluto, they picture a small, distant world somewhere out past Neptune. They know it's far away. They know it used to be called a planet before astronomers reclassified it as a dwarf planet in 2006. But they don't really grasp the distance involved. They don't understand what it means to say that Pluto orbits at an average distance of 3.67 billion miles from the Sun. That number is too large. It doesn't connect to anything in human experience. So let's start by building up to Pluto step by step. Let's understand the distance in a way that makes sense. Earth orbits the Sun at an average distance of about 93 million miles. We call this distance 1 astronomical unit, or AU for short. It's the fundamental measuring stick we use for distances within the solar system. Mars, the next planet out from Earth, orbits at about 1.52 AU. That's roughly 141 million miles from the Sun. The distance between Earth and Mars varies as both planets orbit, but at closest approach, they're about 34 million miles apart. That's the minimum distance a spacecraft would need to travel to reach Mars. Jupiter, the largest planet, orbits at 5.2 AU. That's about 483 million miles from the Sun. Saturn sits at 9.5 AU, about 883 million miles out. Uranus orbits at 19 AU. Neptune, the outermost major planet, is at 30 AU, roughly 2.8 billion miles from the Sun. And then there's Pluto. Pluto's orbit is elliptical and tilted compared to the 8 major planets. At its closest approach to the Sun, called perihelion, Pluto comes in to about 29.7 AU. That's actually closer than Neptune, which is why for 20 years of Pluto's 248-year orbit, it's technically closer to the Sun than Neptune is. At its farthest point, called aphelion, Pluto swings out to 49.3 AU. That's about 4.6 billion miles from the Sun. The average distance is 39.5 AU, 3.67 billion miles. Now, here's where it gets interesting. When we talk about traveling to Pluto, we're not talking about some fixed distance you can just divide by your spacecraft's speed. Space travel doesn't work that way. You can't just point a rocket at Pluto and fly straight there like you're driving to the next town. The distance between Earth and Pluto is constantly changing as both worlds orbit the Sun. Sometimes they're on the same side of the solar system, relatively close. Other times, they're on opposite sides, separated by the full width of their combined orbits. When they're closest, Earth and Pluto are about 28 AU apart. That's roughly 2.6 billion miles. When they're farthest apart, the distance stretches to about 52 AU. That's nearly 4.8 billion miles. The difference between the closest and farthest approach is almost the same as the distance from the Sun to Neptune. But you don't travel in a straight line anyway. Spacecraft follow curved paths called trajectories. These paths are determined by orbital mechanics, by the gravity of the Sun and planets, and by the need to conserve fuel. You launch from Earth, which is moving around the Sun at about 67,000 miles per hour. Your spacecraft inherits that velocity. Then you fire engines to add more speed, accelerating away from Earth and toward your destination. But you're not flying straight to where Pluto is now. You're flying to where Pluto will be when you arrive. You're threading a needle across billions of miles of space, aiming at a moving target that won't reach the intercept point for years. So, how long would it take? The answer depends entirely on how fast you can go and how much fuel you're willing to burn. Let's start with what we've actually done, because that gives us a baseline for understanding the scale of this challenge. The fastest spacecraft we've ever sent to Pluto was New Horizons, launched in January 2006. It left Earth at a higher speed than any previous spacecraft, boosted by an Atlas V rocket with 5 solid rocket strap-on boosters. The launch vehicle delivered so much energy that New Horizons crossed the Moon's orbit in just 9 hours. For comparison, Apollo astronauts took about 3 days to reach the Moon. New Horizons flew past Jupiter 13 months after launch, using Jupiter's gravity to slingshot itself toward Pluto, adding another 9,000 miles per hour to its velocity. This gravity assist was crucial. Without it, the mission would have taken an additional 3 years. The Jupiter encounter demonstrates one of the fundamental techniques for deep space missions, using planetary gravity to accelerate spacecraft without burning fuel. It's elegant and efficient, but requires precise timing. Launch windows that align Earth, Jupiter, and your destination occur only at specific intervals. For Pluto, via Jupiter, these windows open roughly every 12 years. Miss your window, and you wait over a decade for the next one, or you take a longer, slower route that bypasses Jupiter entirely. New Horizons reached Pluto in July 2015, 9.5 years after leaving Earth. 9.5 years. Let that sink in for a moment. Nearly a decade of flight through the void. The spacecraft launched when YouTube was barely a year old, when the iPhone didn't exist. It arrived when smartphones were ubiquitous, when social media had transformed culture, when the world looked entirely different than it did at launch. That's the kind of timescale we're discussing. And that was a relatively small probe, about the size of a grand piano, weighing less than 1,000 pounds without fuel. It carried no humans, no life support systems, no radiation shielding beyond what protected its electronics, no return fuel. It was built for one purpose: to fly past Pluto as fast as possible, take pictures and measurements during a brief closest approach window, and send the data back to Earth over the following months and years. It reached speeds of about 58,000 miles per hour relative to the Sun during the Pluto encounter, making it one of the fastest human-made objects ever. Only the Parker Solar Probe, diving close to the Sun and accelerated by solar gravity, has gone faster. New Horizons carried about 77 pounds of hydrazine fuel, not for acceleration or deceleration, but for course corrections and attitude control. Small thruster burns to adjust trajectory slightly, to point cameras and antennas in the right direction. The spacecraft follows a ballistic trajectory, like a bullet after it leaves the gun. Once the initial acceleration phase ended shortly after launch, New Horizons coasted. It wasn't actively accelerating for most of the 9.5-year journey. It was falling through the Sun's gravity well, gradually slowing as it climbed away from the Sun, but still moving fast enough to reach Pluto in less than a decade. This is important to understand. The speed New Horizons achieved came from its launch velocity plus the Jupiter gravity assist. After that, no more acceleration. It simply coasted for years, crossing billions of miles at slowly decreasing speed as solar gravity pulled back on it. By the time it reached Pluto, it had slowed from its peak velocity near Jupiter, but was still moving at about 31,000 miles per hour relative to Pluto. Far too fast to stop. The spacecraft had no fuel for braking. Slowing down would have required carrying enormous amounts of fuel, which would have made the spacecraft too heavy to launch with available rockets, or would have reduced the mass available for scientific instruments. So New Horizons flew past, snapping photos and collecting data during a brief window measured in hours, then continued into the Kuiper Belt, never to return. Now consider what it would take to send humans. The difference between a flyby probe and a crewed spacecraft is the difference between throwing a rock and building a house. A crewed spacecraft would be vastly larger and heavier, orders of magnitude more complex. You need life support systems to provide oxygen, remove carbon dioxide, maintain temperature and humidity within narrow ranges. The ISS Environmental Control System processes over 10,000 liters of air and recycles about 6 liters of water daily for its crew. Scale that up for a journey of years. Add redundancy in case systems fail, and you're looking at mass measured in tons just for life support. You need water, lots of it, both for drinking, hygiene, and possibly radiation shielding. Humans need about 3 liters of water per day for drinking and food preparation. Add hygiene, and you're at perhaps 5 to 10 liters per person per day. For a crew of 6, on a 7-year mission, even with aggressive recycling, you might need to start with several tons of water. You need food for the entire journey, ideally varied enough to prevent menu fatigue and maintain morale. Freeze-dried meals, vacuum-sealed, with long shelf life. Maybe some ability to grow fresh food, sprouts, or leafy greens in a small hydroponic system. That adds complexity, equipment, and mass. You need sleeping quarters, not just sleeping bags attached to walls like on the ISS, but actual enclosed spaces where crew members can have privacy. Privacy becomes critical on long-duration missions. Design philosophies for long duration. Spacecraft include individual crew quarters, small cabins with sleeping space, personal storage, a screen for entertainment and communication, a door that closes. You need exercise equipment to prevent muscle and bone loss in zero gravity. Resistance machines, treadmills with harnesses, stationary bikes. These machines must function reliably for years. You need spare parts, maintenance supplies, replacement cables, and bands. You need medical supplies sufficient to handle anything from minor injuries to potentially major medical emergencies. Stitches for lacerations, antibiotics for infections, medications for chronic conditions, dental equipment, because tooth problems don't stop in space. Diagnostic tools to assess injuries or illness. Maybe even capability for emergency surgery, though performing surgery in zero gravity presents challenges. Blood doesn't pool, it floats. Anesthesia distribution in the body changes without gravity. Wound healing may be affected. Medical training for crew members becomes essential because you can't call a doctor when you're years from Earth. You need powerful computers and redundant systems in case something fails. Navigation computers to calculate trajectories and course corrections. Communication systems to maintain contact with Earth despite growing light speed delay and signal weakness. Environmental monitoring to track air quality, temperature, humidity, watch for leaks or system failures. Data storage for scientific observations, mission logs, personal files, entertainment, media. All of this hardware must function in vacuum, in temperature extremes, in radiation environment, for years, without professional maintenance facilities. You need radiation shielding, because space beyond Earth's magnetic field is filled with high-energy particles that can damage cells, increase cancer risk, potentially cause acute radiation sickness if exposure is severe enough. The ISS orbits within Earth's magnetosphere, which deflects most charged particles from the solar wind and some cosmic rays. Astronauts on the ISS receive about 0.2 to 0.4 millisieverts per day of radiation exposure. In deep space, beyond the magnetosphere, exposure increases to perhaps 0.6 to 1.5 millisieverts per day, depending on solar activity. Over a 7-year mission that accumulates to a dose exceeding current career limits for astronauts. We need to understand what radiation in space really means. There are several sources and types. Solar energetic particles come from solar flares and coronal mass ejections. The sun periodically erupts, throwing plasma and high-energy particles outward. These events are somewhat predictable, linked to the 11-year solar cycle, but individual flares are sudden. A large solar particle event can deliver dangerous radiation doses within hours. If you're caught in open space without shielding during a major event, you could receive acute radiation, sickness, nausea, fatigue, possible damage to immune system and internal organs. Galactic cosmic rays are even more concerning for long-duration missions. These are high-energy particles, mostly protons and atomic nuclei, accelerated to nearly the speed of light by supernova explosions and other energetic events across the galaxy. They're always present, constantly sleeting through space in all directions. Unlike solar particles, you can't predict when they'll hit because they're coming from all over the galaxy. And they're harder to shield against because they're so energetic. When cosmic rays hit material, they can create showers of secondary particles. A single high-energy cosmic ray hitting an aluminum wall can produce multiple lower-energy particles that scatter into the spacecraft. Some materials create worse secondary showers than others. Hydrogen is actually one of the best shielding materials because hydrogen nuclei, protons, absorb energy without creating many secondary particles. Water, with its 2 hydrogen atoms per molecule, provides decent shielding. Polyethylene, a plastic rich in hydrogen, is even better per unit mass than aluminum. Some spacecraft designs propose lining crew quarters with polyethylene or water tanks. Use consumables, water, and possibly food as dual-purpose shielding. As you consume them during the mission, shielding decreases, but hopefully you're on the return leg by then, getting closer to Earth rather than farther away. Even with shielding, radiation exposure on a Pluto mission would be significant. Crew members would face measurably increased cancer risk over their lifetimes. Not a guarantee of cancer, but statistically elevated probability. NASA's current career exposure limit for astronauts is based on not exceeding a 3% increase in lifetime cancer mortality risk. A multi-year mission to Pluto could push beyond that limit. This creates ethical questions. Do you allow crew members to volunteer for missions that exceed safety guidelines? If they understand the risks and accept them, should we prevent them from going? Different space agencies have different philosophies on acceptable risk. These aren't easy questions with clear answers. And you need fuel, not just to get there, but to slow down when you arrive and potentially return home. This is where the mathematics of spaceflight become brutally unforgiving. New Horizons didn't slow down. It screamed past Pluto at 30,000 miles per hour, taking photos during a brief window of closest approach, then continued into the Kuiper Belt. For a human mission, you'd need to decelerate to match Pluto's orbital velocity so you could actually orbit the dwarf planet, conduct extended observations, possibly land on its surface. That requires fuel. A lot of fuel. The relationship between fuel and payload in rocketry is governed by the Tsiolkovsky rocket equation, named after Russian scientist Konstantin Tsiolkovsky, who derived it in 1897. The equation states that the change in velocity a rocket can achieve depends on the exhaust velocity of its engine and the natural logarithm of the ratio between initial mass and final mass. In practical terms, this means getting exponentially harder as you try to achieve higher speeds or carry more payload. Every kilogram of mass you want to accelerate or decelerate requires fuel. But fuel has mass too, so you need more fuel to accelerate the fuel, which requires even more fuel to accelerate that fuel. It compounds rapidly. To carry enough fuel to both accelerate to Pluto and decelerate upon arrival, you might need a spacecraft where 80 or 90% of the mass at launch is fuel. Only 10 or 20% is actual spacecraft structure, systems, crew, supplies. And if you want to come back to Earth, you need to carry even more fuel to accelerate for the return journey and decelerate when you arrive. The mass ratios become absurd. You might need 95% of your launch mass to be fuel just to make a round trip possible. This is why planetary missions typically use gravity assists and aerobraking instead of carrying all the fuel they'd need. Gravity assists, like New Horizons' Jupiter flyby, use planetary gravity to change velocity without burning fuel. Aerobraking uses a planet's atmosphere to slow down by friction. Mars missions use aerobraking extensively because Mars has enough atmosphere to provide significant drag, but not so much that spacecraft burn up. Pluto has almost no atmosphere, far too thin for aerobraking. And gravity assists require planets to be in the right positions, which constrains launch windows and trajectory options. So, fuel mass becomes the dominant constraint on crewed missions to the outer solar system. Chemical rockets, the type we currently use, burn fuel and oxidizer together, producing hot exhaust gases that exit through a nozzle, generating thrust by Newton's third law. They're powerful, capable of producing enough thrust to lift enormous masses off Earth's surface against gravity. The Saturn V that launched Apollo missions generated 34 million newtons of thrust at liftoff, about 7.6 million pounds force. That's enough to accelerate 2.9 million kilograms, the weight of the fully fueled rocket, upward against Earth's gravity. But chemical rockets are inefficient for interplanetary travel because their exhaust velocity is relatively low. Exhaust velocity, or specific impulse, is the fundamental measure of rocket efficiency. It tells you how much momentum you get per unit of propellant expelled. The best chemical rockets achieve exhaust velocities around 4,500 meters per second, about 10,000 miles per hour. That sounds fast, but it's not great when you're trying to change your velocity by tens of thousands of miles per hour. You end up needing enormous amounts of propellant. The tyranny of the rocket equation means that missions requiring large velocity changes need mass ratios that make the spacecraft impractical. A crewed mission to Pluto using only chemical propulsion would require a spacecraft so massive that no current launch vehicle could lift it. You'd need to assemble it in orbit, from pieces launched separately, which adds complexity, cost, and risk. Or you'd need to develop entirely new heavy-lift rockets, far larger than anything that currently exists. So, what about sending humans with the technology we have right now, today? The brutal truth is that chemical rockets, our only operational propulsion system, make a crewed Pluto mission nearly impossible. A spacecraft, using chemical propulsion and carrying enough fuel to actually stop at Pluto rather than fly past, would require 25 to 30 years just to reach the dwarf planet. One way. That's half a human lifetime spent in transit. The crew members who launched in their 30s would be approaching retirement age when they finally arrived. And we haven't even discussed the return journey. The reason comes down to fuel mass. To reach Pluto and decelerate requires velocity changes totaling tens of thousands of miles per hour. The rocket equation transforms these numbers into propellant requirements so massive that the spacecraft becomes absurd. You might need 95% or more of your launch mass to be fuel. For every ton of useful spacecraft, crew quarters, life support, supplies, you're carrying 19 tons of chemical propellant. The sheer mass makes the vehicle ponderous, slow to accelerate, requiring decades to build up the velocity needed. And carrying that much fuel for decades creates its own problems. Storage tanks add mass. Propellants can degrade over time. Systems must remain functional for the entire journey with no possibility of resupply or major repairs. A crewed mission to Pluto using only chemical rockets would take so long that keeping the crew alive becomes nearly impossible with current life support technology. 25 to 30 years outbound, the same returning. 50 to 60-year missions are beyond anything humanity has attempted or can currently support. This is why space agencies are developing advanced propulsion systems. Not because chemical rockets don't work, they do, but because they simply cannot deliver acceptable performance for deep space crewed missions. The alternatives under development, or proposed, offer dramatically better efficiency, though each comes with its own challenges, and none are flight-ready today. Nuclear thermal propulsion represents the nearest term advanced option. The concept is straightforward. A nuclear reactor heats hydrogen propellant to extreme temperatures, thousands of degrees. The superheated hydrogen expands through a nozzle, producing thrust. Because nuclear reactions release millions of times more energy than chemical reactions, nuclear thermal rockets achieve roughly double the exhaust velocity of chemical systems. Better efficiency means less propellant mass for the same mission. The NERVA program, nuclear engine for rocket vehicle application, actually built and tested these engines in the 1960s and 70s. Engineers at the Nevada test site fired nuclear thermal rockets at full power, demonstrating exhaust velocities exceeding 8,000 meters per second and thrust levels over 50,000 newtons. The engines worked. They ran for hours without failure. They proved the concept was practical with 1960s technology. NERVA was cancelled in 1973, not because of technical failure, but because the Apollo program was ending and planned Mars missions were shelved. Without a clear mission requiring nuclear propulsion, Congress stopped funding development. A modern nuclear thermal rocket could potentially enable a crewed Pluto mission with transit times of 15 to 20 years each way. Still a generation. Still an enormous commitment, but half the duration of chemical propulsion. The spacecraft would burn hydrogen for weeks during departure, building velocity as it climbs away from Earth. Then it would coast for years across the solar system. As it approaches Pluto, the engines would fire again, burning hydrogen to decelerate enough for orbital capture or landing. But nuclear thermal propulsion faces significant challenges beyond the political and regulatory hurdles of launching nuclear reactors into space. Hydrogen is the propellant, and hydrogen must be stored as a cryogenic liquid at -423 degrees Fahrenheit or -253 degrees Celsius. Over a 15 to 20-year journey, hydrogen slowly boils off despite the best insulation. Some mission designs simply accept these losses and carry extra hydrogen to compensate. Others propose active refrigeration systems, but those require continuous electrical power throughout the journey, adding complexity and mass. Nuclear electric propulsion takes a different approach. Instead of using reactor heat directly for thrust, nuclear electric systems generate electricity from a reactor and use that electricity to power ion engines. Ion engines accelerate charged particles, typically xenon ions, to extremely high velocities using electric fields. Exhaust velocities can exceed 40,000 meters per second, nearly 10 times better than chemical rockets. The efficiency advantage is enormous. NASA's Dawn spacecraft demonstrated ion propulsion between 2007 and 2018, visiting both the asteroid Vesta and the dwarf planet Ceres. The mission would have been impossible with chemical propulsion because the required velocity changes exceeded what any reasonable fuel load could provide. Ion engines made it possible by running efficiently for years, accumulating small velocity changes that added up to major trajectory modifications. For a Pluto mission, nuclear electric propulsion could potentially achieve transit times of 12 to 18 years. The spacecraft would accelerate continuously for years, building velocity gradually through patient low thrust. Midway through the journey, it would flip orientation and begin decelerating, arriving at Pluto with low relative velocity. The trade-off is that ion engines produce very low thrust. You can't feel it in your hand. The gentle push must operate continuously for years to achieve meaningful velocity changes. And those ion engines require substantial electrical power. A crewed spacecraft might need tens or hundreds of kilowatts continuously, far more than any space reactor has ever provided. NASA's Kilopower project has developed a 10-kilowatt reactor small enough to fit in a cargo van. Scaling up to 100 kilowatts or more for a crewed mission represents significant engineering development. But the physics is well understood, and the technology appears achievable within a couple decades of focused work. More optimistic scenarios. Imagine advanced nuclear electric systems with higher power reactors and more efficient ion engines, achieving transit times of 10 to 15 years. These systems don't exist even in prototype form. They require substantial development, investment, and decades of work. But they're not science fiction. The underlying principles are sound. The engineering challenges are severe, but appear solvable with sufficient resources and time. Beyond these near-term and mid-term options lie more speculative technologies that might dramatically reduce transit times if they can ever be made to work. Nuclear fusion propulsion could achieve exhaust velocities of hundreds of miles per second by fusing hydrogen isotopes and directing the released energy into thrust. A fusion-powered spacecraft might reach Pluto in 3 to 6 years. The problem is that controlled fusion doesn't exist. We've worked on fusion power for 70 years. Recent experiments have achieved fusion ignition for the first time, proving the physics works. But a practical fusion reactor that produces more energy than it consumes remains decades away. A fusion rocket suitable for spacecraft would require even more development beyond basic power generation. Fusion propulsion might become possible late this century or early next century. Or it might remain forever impractical despite the appealing physics. Antimatter propulsion represents the theoretical limit of rocket efficiency. When matter and antimatter meet, they annihilate completely, converting 100% of mass directly into energy. The energy density is unmatched. A few grams of antimatter could accelerate a massive spacecraft to significant fractions of light speed. Transit to Pluto might take weeks instead of years. But producing antimatter requires particle accelerators and enormous energy inputs. Current global production totals roughly 20 nanograms across all of history. Billionths of a gram. Scaling to the grams or kilograms needed for propulsion would require energy investments exceeding what humanity has ever produced. Antimatter propulsion remains pure science fiction for any foreseeable timeline. The realistic answer to how long it would take to reach Pluto with human crews depends on which technology we're willing to develop and how long we're willing to wait. With chemical rockets, the only system flight ready today, we're looking at 25 to 30 years minimum, probably longer, making such missions completely impractical. With nuclear thermal propulsion, a technology we tested 50 years ago but never developed for flight, 15 to 20 years becomes possible. With nuclear electric systems requiring reactors and ion engines we haven't built yet, 12 to 18 years might be achievable. With advanced systems further in the future, perhaps 10 to 15 years. With fusion propulsion that doesn't exist and may never exist, maybe 3 to 6 years. None of these timelines are comfortable. Even the most optimistic, realistic scenarios require dedicating substantial portions of a human lifetime to the journey. And the faster options require technology development programs spanning decades before the first mission could launch. This is the core challenge that makes Pluto so formidable for human exploration. The propulsion technology we have takes too long. The technology that might work adequately doesn't exist yet and won't for decades. The technology that would make the mission truly practical may never exist at all. Beyond propulsion, spacecraft architecture matters enormously. Designing a ship to keep humans alive and functional for years is its own challenge. The International Space Station provides lessons about long-duration life support, but also reveals limitations. The ISS has grown over more than 2 decades into a modular complex with multiple habitation modules, laboratories, solar arrays, radiators, and docking ports. Its pressurized volume is about 915 cubic meters, roughly equivalent to a 6-bedroom house. That volume supports 6 crew members comfortably, though it's hosted as many as 13 during brief crew overlap periods. For extended duration, you want about 150 cubic meters per person minimum for reasonable quality of life. Less than that, and you're looking at submarine-level confinement, which works for military crews on short deployments but becomes psychologically challenging over years. A spacecraft to Pluto carrying 6 crew might need 1,000 cubic meters of pressurized volume. Multiple modules for sleeping quarters, common areas, exercise space, laboratory work, storage. More volume is better for mental health, but worse for mass and cost. Every cubic meter of pressurized structure requires hull material. strong enough to hold internal pressure against vacuum, thick enough to provide some radiation shielding and micrometeorite protection. Aluminum alloy hull, typical of spacecraft, is about 5 millimeters thick, weighing roughly 14 kilograms per square meter. A cylindrical module, 4 meters in diameter and 10 meters long, provides 125 cubic meters volume with surface area about 140 square meters, weighing nearly 2 tons just for the hull. And you need multiple such modules, plus all the internal systems, equipment, supplies. The spacecraft likely masses in the hundreds of tons, roughly 1,000 times more than New Horizons. Getting that mass moving fast enough to reach Pluto in 12 to 20 years requires enormous fuel if using chemical propulsion. Years of continuous ion thrust powered by nuclear reactors, or high-thrust nuclear thermal engines burning massive quantities of liquid hydrogen. All options require spacecraft much larger than anything currently flying, too large to launch in one piece. It has to be assembled in orbit from components launched separately. Astronauts and robots would connect modules, install systems, integrate propulsion, attach solar panels or reactors, load supplies and fuel over months or years of construction work in space. Artificial gravity becomes important for crew health on multi-year missions. Zero gravity causes muscle atrophy, bone density loss, fluid shifts, vision changes, and cardiovascular deconditioning. Astronauts on the ISS exercise 2 hours daily to slow these effects, but still experience measurable degradation. After 6 months in space, astronauts lose up to 20% of muscle mass and 1 to 2% of bone density. For a mission lasting years, degradation could progress to debilitating levels. Crew members might reach Pluto too weak to function in even 6% gravity. Artificial gravity solves this. Rotating the spacecraft creates centrifugal acceleration that mimics gravity. For one standard Earth gravity, you need appropriate combinations of radius and rotation rate. A small radius requires fast rotation, which creates noticeable Coriolis effects, causing disorientation. Larger radius allows slower rotation with minimal side effects. A radius of 100 meters rotating at about 0.3 revolutions per minute produces comfortable artificial gravity. But building such structures requires significant engineering, likely 2 modules connected by a long truss, spinning around their common center. Even with advanced propulsion, we're looking at multi-year journeys. 10 to 15 years at best, with advanced technology that doesn't exist yet in operational form. More realistically, 15 to 20 years with near-term nuclear systems. Possibly longer with chemical rockets, or if something goes wrong, or if you launch during a less favorable orbital alignment. And that's just one way. If you want to come back, you need to either carry enough fuel for the return journey or refuel at Pluto somehow. Let's think about what this means for the crew. 15 to 20 years in a spacecraft, minimum. Not 15 to 20 years on a planet where you can walk around, breathe fresh air, see the sky. 15 to 20 years in a metal tube, in zero gravity, breathing recycled air, eating preserved food. Every moment, dependent on machines to keep you alive. The longest anyone has spent in space continuously is about 14 months, achieved by Russian cosmonaut Valery Polyakov aboard the Mir space station in the mid-1990s. Astronauts on the International Space Station typically spend about 6 months in orbit before returning to Earth. Even that relatively short duration causes significant physiological changes. Muscles atrophy without gravity to work against. Bones lose density, leaching calcium at rates of about 1% per month. The heart weakens because it doesn't have to pump blood upward against gravity. Vision can deteriorate as fluids shift toward the head, increasing pressure on the optic nerves. The immune system becomes less effective. Wounds heal more slowly. And those effects are from low Earth orbit, still within Earth's magnetic field, which provides some protection from cosmic radiation. Beyond that protective bubble, radiation exposure increases dramatically. Galactic cosmic rays, high-energy particles from supernovae and other cosmic sources, constantly sleeting through space. Solar particle events, bursts of radiation from the sun during solar flares and coronal mass ejections. On Earth, we're shielded by the atmosphere and the magnetic field. In deep space, there's nothing between you and the radiation. Spacecraft walls provide some shielding, but not enough. Aluminum, the most common spacecraft structural material, actually makes things worse in some cases. When cosmic rays hit aluminum atoms, they create secondary particles that can be more damaging than the original radiation. Water is a better shield. Hydrogen atoms in water molecules are effective at absorbing high-energy particles. Some spacecraft designs propose surrounding crew quarters with water tanks, using the water supply as makeshift radiation shielding. But water is heavy. Every liter weighs a kilogram, and you need meters of water to provide meaningful protection. The mass adds up fast. Even with shielding, astronauts on a multi-year mission would receive radiation doses far exceeding current safety limits. NASA's current career limit for astronauts is based on acceptable risk of cancer mortality over a lifetime. A mission to Pluto would likely exceed this limit significantly. We're talking about accepting a measurably increased cancer risk for anyone who makes the journey. Not certain death, but a real, quantifiable reduction in life expectancy. That's a trade every crew member would have to understand and accept. Then there's the psychological challenge, which might be the hardest part of all. Isolation, confinement, monotony, distance from everything and everyone you've ever known. You're in a small space with the same few people for years. Day after day, week after week, month after month. The same faces, the same voices, the same environment. You can't go outside for a walk. You can't get fresh air or see a horizon or feel rain on your face or wind in your hair. You can't visit friends or family. You can't escape to somewhere quiet when you need solitude beyond your tiny cabin. The longest anyone has spent in space continuously is 437 days, achieved by Russian cosmonaut Valery Polyakov aboard the Mir space station from January 1994 to March 1995. Polyakov volunteered specifically to demonstrate that humans could psychologically handle the duration needed for a Mars mission. He succeeded, returning to Earth in reasonable mental and physical condition, though he later said the experience was incredibly challenging. He described the psychological difficulty of knowing you can't leave, you can't go home, must continue, regardless of how you feel. Astronauts on the International Space Station typically spend about 6 months in orbit before returning to Earth. Many report that the first month or two is exciting, novel, full of wonder at the experience of weightlessness and the view of Earth. By month 3 or 4, the novelty has worn off. You're adapted to the routine, no longer surprised by floating or by the view. The day-to-day work becomes just work, maintenance tasks and experiments and exercise filling the schedule. By month 5 or 6, many crew members report feeling ready to go home, missing Earth, missing family, craving simple things like taking a shower with real running water, or eating fresh food, or walking on grass. 6 months is nothing compared to the years required for Pluto. The psychological adaptation needed for multi-year missions is unexplored territory for humans. We have some data from Antarctic research stations where crews winter over in isolation for 8 to 10 months during the polar night when it's too dangerous for planes to land. Antarctic winter over crews typically number 15 to 50 people, more than a spacecraft crew, providing more social variety. Even so, psychological challenges are well documented. Cabin fever, interpersonal conflicts, depression, disrupted sleep patterns, difficulty concentrating. These effects appear despite screening for psychological resilience and despite support from mission psychologists who conduct video counseling sessions. A spacecraft to Pluto would be smaller than an Antarctic station and isolated for far longer. Communication with Earth has a time delay that grows as you move farther from home. Light speed sets an absolute limit on how fast information can travel. At Earth's distance from the Sun, 1 AU, light takes about 8 minutes to reach Earth from the Sun. At 2 AU, about 16 minutes. The delay is proportional to distance. For Pluto at 39 AU, radio signals take about 5.5 hours to travel one way. That's an 11-hour round-trip delay for any conversation. You can't have real-time dialogue. You send a message, wait 11 hours, maybe get a reply. By the time you receive it, the context might have changed. Your mood might be different. The problem might have evolved or resolved on its own. Imagine trying to maintain relationships under those conditions. You message your family on Earth. They respond 11 hours later. Their response addresses what you said 11 hours ago, not your current state. You reply to their message. They get it 11 hours later. This back and forth continues, each exchange taking half a day. A simple conversation that would take 5 minutes in person stretches over several days. As you travel farther, the delay increases. Midway to Pluto, at about 20 AU, the round-trip time is about 5.5 hours. When you finally reach Pluto, you're dealing with that full 11-hour delay. Any emergency, any crisis requiring input from Earth takes 11 hours before you even get a response. By then, you've likely had to handle it yourself, or the situation has deteriorated beyond help. This creates profound psychological pressure. You're truly on your own, in a way few humans have ever experienced. Antarctic researchers can at least call for rescue in emergencies, even if it takes days to arrive. Spacecraft crews have no such option. Help is months or years away. You solve problems yourself, or you don't solve them. Crew selection becomes critical. You need people who are not just technically skilled, but psychologically robust, capable of handling stress, isolation, and confinement without breaking down. They need to work well together, resolve conflicts constructively, support each other through difficult periods. Personality clashes that would be minor annoyances in normal life become serious problems when there's no escape. Space agencies have decades of experience selecting astronauts for short-duration missions. The process is rigorous, involving psychological testing, interviews, team exercises, simulations. They're looking for people who are competent, calm under pressure, good team players, able to take direction, but also think independently when needed. For a multi-year mission, the standards would be even higher and the evaluation even more thorough. You'd want crew members who've already flown in space, who've proven they can handle the environment. You'd want psychological profiles that show resilience, emotional stability, low conflict tendency. You'd want people who genuinely get along, who've worked together before, who've demonstrated they can resolve disputes without mission controllers mediating. Some mission architectures propose sending couples or even families, the idea being that existing strong relationships might provide better psychological support than relationships formed for the mission. A married couple knows how to support each other, resolve conflicts, maintain connection under stress. Of course, this creates challenges if relationships deteriorate during the mission, and biological realities around reproduction in space need addressing through policies on contraception or crew selection. Though pregnancy in space is completely unstudied in humans and would be extraordinarily risky, entertainment and activity become essential for mental health. You need ways to occupy your time beyond work tasks. Movies, shows, music, books, games, all stored digitally and accessible on personal devices. Crew members would bring their own libraries, share favorites, watch things together as social activities. Communication with Earth, despite the delay, provides connection to home. Video messages from family and friends. News updates about what's happening on Earth, though events are 11 hours old by the time you see them. Maybe even delayed participation in events, watching sports games, or concerts that happened hours before. Hobbies and creative pursuits help fill time. Writing, painting, drawing, photography of space and the spacecraft, learning new skills or languages, studying topics unrelated to the mission. Some crew members might maintain blogs or journals documenting the experience. Others might engage in research that's not part of the primary mission, conducting observations or experiments that interest them personally. Exercise fills substantial time, 2 hours daily, just to maintain muscle and bone. But it's also psychologically valuable, providing routine, accomplishment, a sense of doing something positive for your health. Many astronauts report that exercise becomes meditative, time to think or not think, to process emotions, to work through problems mentally while the body is engaged. Still, even with all these coping mechanisms, years of confinement will take a toll. Most crew members will experience periods of depression, anxiety, irritability, sleep disruption. Some might experience more serious psychological issues. The question isn't whether problems will occur, but how severe they'll be, and whether the crew and mission controllers can manage them. Medical capabilities on board become important not just for physical injuries, but for mental health. One crew member should have psychiatric training, capable of providing counseling and support. Medications for depression and anxiety should be available. Communication protocols should exist for crew to speak confidentially with psychologists on Earth despite the time delay. Asynchronous therapy via recorded messages isn't ideal, but it's better than nothing. And there's the reality that things will go wrong. Not just might go wrong, will go wrong. Equipment fails. Systems malfunction. People get sick. Accidents happen. The question isn't if, but when and how severe. Murphy's Law applies fully to spacecraft. Anything that can fail eventually will fail. Pumps wear out, Seals degrade. Electronics suffer radiation damage. Moving parts break. You prepare for this as best you can. You bring spares for critical components, multiple spares for things that fail often. You cross-train crew members so multiple people can perform essential tasks. If the medical officer is injured or ill, someone else needs to be able to provide care. If the engineer who maintains the life support system becomes incapacitated, others need to know enough to keep it running. You design systems with redundancy. 2 independent air recycling systems. So if one fails, the other keeps the crew alive while you fix the broken one. Backup generators, backup computers, backup communication, antennas. The ISS has extensive redundancy because failures do occur and you can't always get replacement parts quickly, even in low Earth orbit. For a Pluto mission, there are no replacement parts coming. You have what you launched with, nothing more. Medical preparation involves bringing extensive supplies and equipment. Medications with long shelf lives, antibiotics, pain relievers, anti-inflammatory drugs, medications for chronic conditions crew members might have, surgical tools in case emergency procedures become necessary, sutures, scalpels, anesthetics, though performing surgery in zero gravity presents serious challenges. Diagnostic equipment to assess injuries and illnesses, blood testing, imaging. If possible, though portable ultrasound is more realistic than X-ray or MRI for mass constraints. Dental equipment, because tooth problems don't stop happening just because you're in space, and a severe tooth abscess or broken tooth can be debilitating. But there are limits to what medical care can be provided. A major traumatic injury, internal bleeding from an accident, might be beyond what the crew can treat. A serious illness requiring specialized equipment or interventions not available on the spacecraft could be fatal. Heart attack, stroke, appendicitis, cancer. All are possibilities over a multi-year mission with crew members who might be in their 40s or 50s. Screening can reduce risk, but can't eliminate it. This creates ethical dilemmas. If a crew member develops a serious condition that can't be treated, what happens? Do you attempt to return early, cutting the mission short, possibly dooming it to failure? Do you continue to Pluto while providing comfort care? Do you allow the person to choose how they want to proceed? These are questions mission planners have to consider, protocols to establish, even though everyone hopes they'll never be needed. Crew members volunteering for such missions know the risks. They understand that medical help is limited, that rescue is impossible, that some situations might be unsurvivable. They accept this as part of the deal, the price of being among the first humans to travel to the outer solar system. But knowing abstractly that you might face life-threatening situations and actually dealing with one when it happens are different things psychologically. The journey to Pluto isn't a tourist excursion or a simple transportation problem. It's an expedition into genuinely hostile environment where small mistakes can be fatal and bad luck might be equally deadly. It requires people willing to accept substantial personal risk for goals that might seem abstract to others, the advancement of human knowledge and capability, the expansion of human presence into the cosmos. Not everyone is wired that way, and that's perfectly fine. Most people reasonably prefer comfort, safety, proximity to family and friends. They have no desire to spend years in a metal can crossing billions of miles of void. That's a rational choice. But some people are different. Some people hear about the challenges and risks and dangers, and their response is to want to go anyway, to be part of something bigger than themselves, to push boundaries, to go where nobody has gone. Throughout history, these people have explored the frontiers, climbed the mountains, crossed the oceans, mapped the continents. They didn't do it because it was safe or comfortable or profitable. They did it because it was there, because it was possible, because someone had to go first. Those are the people who'll crew the first mission to Pluto when it happens, if it happens. And that's a genuine if. We shouldn't assume human missions to the outer solar system are inevitable. They might never occur. We might decide the costs are too high, the risks too severe, the scientific return inadequate compared to robotic missions. We might focus our crewed exploration efforts elsewhere, Mars and the Moon and near-Earth asteroids, leaving the outer system to robots. That's a legitimate choice. Or we might develop the technology and infrastructure over the coming century that makes Pluto missions routine, commercial, accessible to private organizations or individuals wealthy enough to fund them. Imagine a future where there are permanent settlements on Mars, where asteroid mining provides resources, where fusion power makes energy cheap and abundant, where launch costs have dropped by orders of magnitude. In that future, maybe Pluto is just another destination, reachable in a few years with acceptable risk. The path from here to there isn't clear. It requires sustained effort over decades, continued investment in space technology, solving the hard problems one at a time. Propulsion, life support, radiation protection, psychological support, medical capabilities, all need to advance significantly. Some advances will come from targeted development specifically for space applications. Others might come from unrelated fields, materials, science, or biotechnology, or computing that happen to enable new space capabilities. We can't predict exactly how it will happen or when, but we can say that the fundamental physics allows it. Pluto is far, but not unreachably far. The challenges are severe but not unsurmountable with sufficient resources and determination. Whether we choose to make that investment, whether we decide Pluto is worth the cost and risk, that's a social and political question, not a technical one. There's also the question of why. Why send humans to Pluto when robots can do most of the science cheaper and safer? This question comes up for every proposed crewed mission beyond low Earth orbit. The practical arguments for human presence are real but debatable. Humans are more flexible and adaptable than robots, can respond to unexpected situations, make judgment calls, perform complex tasks that would take years to program and test for autonomous systems. Humans can do in an hour what might take a robot weeks. But robots are getting better. Machine learning and AI are advancing rapidly. The gap between human and robotic capability in space narrows over time. Maybe by the time we have the technology for crewed Pluto missions, robots will be sophisticated enough that human presence adds little scientific value. Or maybe there will always be tasks humans do better, insights humans spot that automated systems miss. It's hard to predict. The less tangible arguments for human exploration might be more compelling in the long run. Inspiration, cultural impact, the psychological satisfaction of knowing humans have reached the boundaries of our solar system with their own presence, not just by proxy through machines. When Neil Armstrong stepped onto the moon, it inspired millions, changed how humanity saw itself, demonstrated that ancient dreams of reaching other worlds weren't fantasy but achievable reality. The scientific return from Apollo was valuable, certainly, but the cultural impact arguably exceeded the scientific value. A human mission to Pluto could have similar cultural resonance. It would represent the farthest reach of human exploration, pushing the boundary of where we've been with our own bodies, our own eyes. It would demonstrate that the solar system, vast as it is, lies within our grasp, that we're not confined to one planet or even the inner solar system, that, with enough effort and ingenuity, we can go anywhere our spacecraft can reach. That knowledge changes the collective human self-conception. We become a species capable of crossing our solar system. It shifts the frame from Earth bound to solar system present. Over generations, that psychological shift might enable developments we can't imagine, settlements on distant worlds, resource extraction from Kuiper Belt objects, scientific outposts throughout the planetary system. Or maybe none of that happens. Maybe the first human mission to Pluto is also the last, a one-time achievement like Apollo, concluded after demonstrating it can be done and then abandoned when priorities shift. Exploration isn't inevitable or irreversible. It requires sustained will and resources. So when we ask how long it would take to reach Pluto, we're really asking a cluster of questions. How long with current technology? How long with near-term improvements? How long with hypothetical, far-future systems? And implicitly, when will we actually attempt it? The answers are 9.5 years for a flyby with current technology, 15 to 20 years for crewed missions with near-term nuclear thermal propulsion, 12 to 18 years with nuclear electric systems that don't exist yet, possibly 10 to 15 years with advanced systems further in the future. But the when question has no technical answer. It's entirely about human choices, political will, resource allocation, cultural priorities. We could start developing the technology seriously today if we chose to commit the resources. In 20 or 30 years, we might have operational systems capable of crewed outer solar system missions. Or we might decide it's not a priority and focus elsewhere, and it never happens within our lifetimes. What we know for certain is that the universe doesn't care about our timelines or priorities. Pluto will orbit the Sun for billions of years, indifferent to whether humans visit. The opportunity exists in the physical possibility. Whether we seize it is up to us. And that brings us back to the fundamental question of exploration. Why go? Not the practical justifications or scientific rationale, but the deeper drive. Humans have always explored because we're curious, because we want to know what's over the horizon, because we're not satisfied with staying in familiar territory. That drive has led us across continents, across oceans, eventually into space. It's brought us to the moon, sent our robots to every planet, reached the edge of the solar system with Voyager. Pluto represents a frontier in that ongoing story. It's one of the most distant places in our solar system. We might realistically visit with human missions in the foreseeable future. Beyond Pluto lies the Kuiper Belt, tens of thousands of icy objects, a vast unexplored region extending perhaps 50 AU from the Sun. Beyond that is the scattered disk, objects on eccentric orbits possibly stretching to 100 AU or more. And beyond that, the Oort cloud, a spherical shell of comets possibly extending halfway to the nearest stars. But those regions are so distant, so diffuse, that human exploration becomes impractical with any technology we can currently envision. Pluto sits at the boundary of the practical, the farthest point where we can imagine sending humans with conceivable technology and returning them within their lifetimes. It represents the edge of what's possible, which is exactly why it's compelling. The journey would test everything we know about keeping humans alive in space. It would require advances in technology, medicine, psychology, engineering. It would cost enormous amounts of money and carry real risks of failure and loss of life. And in return, we'd gain knowledge about a distant world, about ourselves, about our capabilities and limits. We'd extend human presence to the edge of the planetary system. We'd prove it can be done. Is that worth the cost? Each person answers differently based on their values and priorities. There's no objectively correct answer. But for those who value exploration, who believe humanity's future includes expanding beyond Earth, who want to see how far we can go, the answer is yes. The journey is worth it, not despite the challenges, but because of them. Because hard things are worth doing. Because pushing boundaries reveals what we're capable of. Because reaching Pluto would mean we're no longer confined to the inner solar system, no longer limited to places where the sun is a warm disk in the sky. We'd be a species that can survive and operate in the cold outer darkness, where the sun is just a bright star and Earth is invisible without telescopes. That's a different kind of future than staying close to home. It's a future with more possibilities, more potential, more room for humanity to grow and evolve. Whether we choose that future remains to be seen. The technology will develop if we invest in it. The missions will happen if we commit to them. Humans will walk on Pluto if we decide it's worth the effort. Until then, Pluto remains what it's been for billions of years. A world at the edge of the solar system. Frozen, distant, waiting. Not caring whether we come or not. Just being, following its orbit, evolving slowly over geological time. But if we do go, if humans finally make that journey, stand on that frozen surface and look up at Charon hanging motionless overhead, see Earth as a pale dot barely distinguishable from background stars, feel the cold seeping through layers of insulation, experience 6% gravity, making every movement strange. That moment will justify the years of travel, the billions spent, the risks taken. Not because of any practical benefit, but because it will mean we did it. We reached the edge. We didn't stop at Mars, or the asteroids, or Jupiter's moons. We kept going until we ran out of reasonable places to go in the solar system we were born in. And maybe that's enough. Maybe proving we can do it, demonstrating that distance, however vast, cannot contain us indefinitely, is the point. The journey to Pluto, when it happens, will be as much about human capability and determination as about the destination itself. About showing that we can keep people alive for years, crossing billions of miles. About solving every technical challenge that stands between here and there. About choosing to go, even when it's hard, especially when it's hard. How long would it take to reach Pluto? Years of transit time. Decades of development before launch. Maybe centuries from now to when we're ready as a civilization. But however long it takes, the journey begins with understanding what it would require, appreciating the scale of the challenge, and deciding whether we're willing to commit. That decision point hasn't arrived yet. We're still figuring out how to sustain human presence on Mars, much closer and more accessible. We're still developing the propulsion systems, the life support, the radiation protection. We're still learning how to keep people psychologically healthy for multi-year missions. But we're making progress. Each Mars mission, each long-duration stay on the ISS, each advance in propulsion technology brings us incrementally closer to the capability needed for Pluto. Not rushing toward it necessarily, but building the foundation. And someday, maybe, someone will propose it seriously. Not as a fantasy or thought experiment, but as an actual mission with funding and timelines and crew selection. They'll build the spacecraft, test the systems, train the crew. And those crew members will say goodbye to Earth, knowing they won't see it up close for a decade or more, knowing they might never return at all. And they'll go anyway. Because they're the kind of people who answer, how long would it take to reach Pluto, not with despair at the duration, but with determination to make the journey. Now, let's talk about what happens when you finally arrive. After years of travel, after months or years of acceleration, followed by years of coasting or deceleration, you finally reach Pluto's orbit. The dwarf planet comes into view, growing from a point of light to a disk to a world with visible features. What do you find? A frozen world at the edge of the solar system, where the sun appears as just a bright star, no longer the familiar disk that dominates Earth's sky. The sun from Pluto is still the brightest object in the sky by far, about 250 times brighter than the full moon appears from Earth. Bright enough to read by, to see clearly, to cast distinct shadows. But it's a point source, not a disk. You can't see solar features like you might from Earth through a telescope. It's just an intensely bright star. Pluto receives about 1/1600th the sunlight Earth does. The surface illumination is similar to civil twilight on Earth, that brief period after sunset when the sun is just below the horizon, but the sky still holds significant light. Dim compared to midday on Earth, but not the pitch darkness people sometimes imagine. Your eyes adapt. Colors become muted in the reduced light, but you can see the landscape, the variations in surface brightness, the contrast between ices and darker terrain. For detailed work, for EVAs on the surface, you'd use artificial lighting. Helmet-mounted lamps, floodlights on landing vehicles, illumination for cameras and instruments. The sun provides enough ambient light for general visibility, but not enough for close work or scientific investigation. Temperatures on Pluto's surface are brutal by Earth standards. They range from about -375 degrees Fahrenheit to -400 degrees Fahrenheit, roughly -225 to -240 degrees Celsius. At these temperatures, nitrogen, methane, and carbon monoxide, which are gases in Earth's atmosphere, freeze solid. Nitrogen ice dominates Pluto's surface in many regions. In the vast plain called Sputnik Planitia, within Tombor Regio, nitrogen ice fills an impact basin nearly 1,000 miles across. This ice is relatively fresh-looking, smooth, with few craters, suggesting it's geologically young, perhaps only a few 100,000 or million years old. The ice flows slowly over time, scales of hundreds of thousands of years, driven by convection. Warmer, less dense nitrogen ice deep in the basin rises slowly toward the surface, while colder, denser surface ice sinks, creating convection cells visible as polygonal patterns across the plain. Each polygon is 15 to 25 miles across, outlined by troughs where ice is sinking. The process is similar to convection in Earth's mantle, but much faster and on a smaller scale. Mountain ranges rise at Pluto's horizon. Norgay Montes and Hillary Montes, named after the first climbers to summit Mount Everest, reach heights of 2 to 3.5 miles. But these mountains aren't made of rock. They're water ice, frozen harder than steel at Pluto's temperatures. Water ice at -233 degrees Celsius is as rigid as rock at room temperature on Earth. It doesn't flow or deform easily. It can support enormous topographic relief. How these mountains formed is still debated. They might be blocks of ancient crust floating on denser nitrogen ice, buoyed up like icebergs. They might be remnants of ice ejected during the impact that created Sputnik Planitia. Or they might have formed through cryovolcanic processes, ice erupted from the interior and frozen in mountainous forms. To the east of Sputnik, Planitia lies bladed terrain, strange formations unlike anything on Earth. Methane ice has eroded into sharp ridges hundreds of feet high, aligned roughly north-south. The ridges look like rows of enormous knife blades sticking up from the surface. The formation mechanism isn't fully understood. It might involve preferential sublimation, methane ice vaporizing more in some areas than others due to sunlight angle, creating relief over millions of years. Or it might be related to atmospheric deposition, methane frost accumulating in patterns dictated by winds and temperature. Pluto has an atmosphere, thin but measurable. Surface pressure is about 100,000 times lower than Earth's atmosphere, roughly 10 microbars compared to Earth's 1,000 millibars. It's essentially vacuum from a human standpoint. You can't breathe it. A spacesuit on Pluto needs to provide full pressure, oxygen, temperature control, the same as EVAs in space. The atmosphere is mostly nitrogen, with a few percent methane and traces of carbon monoxide. It extends surprisingly high, reaching hundreds of miles above the surface, though it's incredibly tenuous even by Pluto standards. The atmosphere creates haze layers, visible in images from New Horizons. Sunlight breaks apart methane molecules through photochemistry. The fragments combine into more complex hydrocarbons, tholins, which form microscopic particles that scatter light, creating haze. The haze gives Pluto's atmosphere a blue tinge when viewed against the darkness of space, similar to Earth's blue sky, but for different reasons. Earth's sky is blue because air molecules scatter blue light more than red. Pluto's blue haze comes from the scattering properties of organic particles. Walking on Pluto would feel surreal. Gravity is just 6% of Earth's. If you weigh 150 pounds on Earth, you'd weigh 9 pounds on Pluto. Every step would launch you upward. On Earth's moon, which has 16% Earth gravity, astronauts developed a bouncing gait, pushing off lightly and soaring several feet with each step. On Pluto, with even lower gravity, you'd soar higher and farther. A gentle push might send you 10 or 15 feet up, arcing slowly through the thin atmosphere before descending back to the surface over several seconds. Movement would require learning new motor skills. Too much force, and you launch yourself uncontrollably. Too little, and you struggle to overcome inertia in your massive spacesuit. Finding the balance would take practice. Early EVAs would be cautious, crew members moving slowly, testing their ability to control motion in the low gravity. Safety lines might be used near the lander or base to prevent accidentally jumping so hard you reach escape velocity. Pluto's escape velocity is about 3,000 feet per second, far too high to achieve by jumping. But in 6% gravity, intuition about how hard to push off doesn't apply. You'd need to retrain your reflexes. What would you actually do during EVAs? Scientific exploration, primarily. Collect samples of different ices, nitrogen, methane, water. Look for organic materials, study composition and structure. Deploy instruments, seismometers, to study Pluto's interior through moonquakes or Charonquakes. Ground-penetrating radar to probe for subsurface layers. Perhaps a liquid water ocean beneath the crust. Set up long-term monitoring stations, weather sensors to track atmospheric changes, cameras to document seasonal evolution as Pluto progresses through its long year. Pluto takes 248 Earth years to orbit the Sun. It was discovered in 1930 and won't complete a full orbit since discovery until 2178. Seasons on Pluto last decades. Currently, Pluto is moving away from perihelion, where it was closest to the Sun in 1989. As it moves farther out, solar heating decreases slightly. Surface ices sublimate less. The atmosphere may be slowly freezing out and settling back to the surface. By the time Pluto reaches aphelion in the 2130s, much of the atmosphere might have collapsed, leaving only a thin exosphere. Then, as Pluto swings back toward the Sun over the following century, the cycle reverses. Ices warm, sublimate, and the atmosphere builds again. Long-term presence on Pluto would allow studying these changes directly. Not over a few hours, like New Horizons, but over years or decades, watching how the surface and atmosphere evolve. It's the kind of research you can't do with flyby missions or even short-duration visits. You need to be there for extended periods, monitoring continuously, documenting changes. Charon, Pluto's largest moon, dominates the sky if you're on the hemisphere facing it. Charon has about half Pluto's diameter, about 750 miles across compared to Pluto's 1,470 miles. Mass is about 1/8 of Pluto's mass. The two are tidally locked, each always showing the same face to the other, orbiting a common center of mass every 6.4 days. From Pluto's surface, on the Charon-facing hemisphere, Charon hangs motionless in the sky. It doesn't rise or set. It's always visible, always in the same position relative to the horizon, though it goes through phases as Pluto orbits the Sun and the Sun's angle changes. Charon appears much larger in Pluto's sky than Earth's moon appears from Earth. The moon subtends about half a degree as seen from Earth. Charon subtends about 3.7 degrees from Pluto, more than 7 times the angular diameter. It's huge, filling a significant portion of the sky, showing clear surface features even to the naked eye. You'd see its reddish polar cap, thought to be tholins deposited from escaped Pluto atmosphere molecules that get captured by Charon's gravity and frozen onto the cold polar regions. You'd see the equatorial dark belt, darker material, possibly related to cryovolcanic activity in Charon's past. You'd see large craters, scars from impacts over billions of years. From the opposite hemisphere of Pluto, the side facing away from Charon, you'd never see Charon at all. It's permanently below the horizon. If you wanted to observe Charon, you'd have to travel to the Charon-facing hemisphere. This creates 2 distinct regions on Pluto, defined by whether Charon is visible. The Charon-facing hemisphere has a large moon visible in the sky constantly. The far hemisphere has no large moon, just smaller moons, Styx, Nix, Kerberos, and Hydra, occasionally visible as bright points. Those smaller moons are tiny. Nix and Hydra are about 30 miles across. Kerberos is roughly 7 miles, Styx, about 6 miles. Their irregular shapes probably captured Kuiper Belt objects or fragments from the impact that formed the Pluto-Charon system. They orbit farther out than Charon, taking longer to complete their orbits, 20 to 38 days depending on the moon. From Pluto's surface, they'd be visible as stars, brighter than the surrounding background, but not showing disks to the naked eye. Through a telescope, you'd see their irregular shapes and possibly distinguish surface features. Establishing a base on Pluto would be an extraordinary engineering challenge. You'd need habitats that can withstand the temperature extremes, maintain pressure and temperature for crew survival, protect against radiation and micrometeorites. Inflatable modules might work, brought compressed in spacecraft and expanded on the surface. Rigid modules, built from metal or composite materials, might be more durable but harder to transport. Either way, you're constructing pressure vessels that keep -400-degree exterior environment outside while maintaining room temperature inside. That requires serious insulation, probably multiple layers with vacuum gaps similar to thermos bottles. Power generation becomes a challenge. Solar panels work, but with only 1/1600th of Earth's solar intensity, you need large arrays to generate meaningful power. And during Pluto's long night, lasting over 3 Earth days in most locations, solar power drops to 0. Batteries could store energy for night periods, but cycling charge and discharge daily over years degrades them. Nuclear power makes more sense. RTGs, or small reactors, could provide continuous power regardless of sunlight. The reactor, or RTG itself, would sit at some distance from the habitats to minimize radiation exposure. Power cables would connect it to the base. Creating consumables locally would reduce dependence on supply missions from Earth. Pluto has abundant water ice in its crust and possibly subsurface ocean. If you can access it, you can electrolyze water into hydrogen and oxygen. Oxygen for breathing, hydrogen potentially for fuel, or combining with carbon dioxide to make methane for other uses. Pluto's atmosphere contains nitrogen, which could be extracted and stored for pressure maintenance in habitats. Atmospheric processing equipment could compress tenuous atmosphere, freeze it, purify it, liquefy it for storage. Growing food locally is questionable. Plants need light, lots of it, more than sunlight at Pluto provides. You'd need artificial lighting powered by nuclear generators. You'd need soil or hydroponic systems, water, nutrients, temperature control, carbon dioxide supply. The infrastructure, mass, and energy requirements might exceed what's practical compared to just bringing food from Earth. Maybe small-scale greenhouse for fresh greens to supplement preserved food provides psychological benefit. Full self-sufficiency in food production seems unlikely without major investment in agricultural infrastructure. Resource extraction could be valuable for propellant if you're planning to leave Pluto and want to refuel locally instead of bringing all return fuel from Earth. Water ice can be melted and electrolyzed into hydrogen and oxygen, useful propellants for chemical rockets. Nitrogen and methane on the surface could potentially be harvested, though their utility depends on propulsion system used. Mining ice on Pluto isn't fundamentally different from mining ice anywhere. You excavate it, melt it, process it. The challenge is operating equipment at -400 degrees, where most lubricants freeze solid and many materials become brittle. Everything has to be designed for extreme cold, tested thoroughly, because field repairs in such conditions would be incredibly difficult. And then what? You've studied Pluto. You've collected data. Do you return to Earth? That requires fuel, lots of it. You need to accelerate up to speed for the return journey, then decelerate when you reach Earth. If you didn't bring enough fuel for a return trip, you're stranded. Maybe you brought fuel, but you're using it to keep life support running longer than planned because something broke. Trade-offs. Every decision in space involves trade-offs between mass, fuel, time, and safety. Alternatively, maybe you don't return. Maybe this is a one-way mission. You establish a permanent outpost, a research station on Pluto, but maintaining that outpost requires continuous supply missions from Earth. Every few years, a new ship arrives with fresh food, replacement parts, maybe new crew members, to relieve those who've been there longest. Except those ships take years to arrive, and they're expensive. Launch costs, construction costs, operational costs. Billions of dollars per mission. How long can you sustain that? How many missions can you afford before funding runs out or political support evaporates? One of the uncomfortable truths about space exploration is that it's extraordinarily expensive with uncertain return on investment. The Apollo program cost about $130 billion in today's money. It put 12 humans on the moon over 3 years. Then it ended. Not because we'd learned everything there was to learn about the moon, but because the political will and funding disappeared. A mission to Pluto would cost vastly more than Apollo. We're talking about developing new propulsion systems, new life support technologies, new radiation shielding, new long-duration spacecraft, all of which requires research, testing, iteration, then building the actual spacecraft, likely multiple ships for redundancy, then launching them, operating them, supporting them for years or decades. The total cost would easily exceed $1 trillion, possibly several trillion, depending on how it's done. And for what? Scientific knowledge, certainly. Pushing the boundaries of human exploration, absolutely. Demonstrating that we can do it, proving it's possible, yes. But is that worth $1 trillion? Reasonable people disagree. Some argue we should focus resources on problems here on Earth: climate change, poverty, disease, infrastructure. Others argue that exploration defines humanity, that we've always pushed beyond known boundaries, and that the technologies developed for such missions have spin-off benefits we can't predict. Both perspectives have merit. There's also the question of why send humans at all. Robotic probes can do much of the science, cheaper, safer, without risking lives. New Horizons cost about $700 million and returned extraordinary data. A crewed mission would cost 1,000 times more and expose people to years of radiation, isolation, and danger. Is the added value of having humans present worth the added cost and risk? The case for humans includes flexibility and adaptability. Robots are limited by their programming and instruments. Humans can improvise, respond to unexpected discoveries, make judgment calls. A human geologist on Pluto could explore in ways a rover cannot. Humans can repair equipment, reroute power, repurpose tools. When Apollo 13's carbon dioxide scrubbers failed, the crew built makeshift replacements using materials on hand. A robot couldn't have done that. There's also the inspiration factor. Human space exploration captures public imagination in ways robotic missions don't. Apollo inspired millions, drove interest in science and engineering, created a sense of shared human achievement. A mission to Pluto could do the same. But inspiration is hard to quantify, hard to justify in budget negotiations. So we come back to the original question. How long would it take to reach Pluto? With current technology, 9.5 years for a flyby mission like New Horizons. With chemical rockets for a crewed mission that needs to stop, 25 to 30 years minimum. With nuclear thermal propulsion, we could develop 15 to 20 years. With nuclear electric systems requiring reactors we haven't built, 12 to 18 years. With advanced systems further in the future, maybe 10 to 15 years. With fusion technology that doesn't exist, perhaps 3 to 6 years. But the travel time is only part of the challenge. The real question is whether we can build spacecraft that keep humans alive and healthy for that long. Whether we can shield them from radiation effectively. Whether we can prevent the muscle and bone loss that comes with years in zero gravity. Whether we can maintain psychological health in isolation and confinement. Whether we can afford the cost. And whether we can build the political will to sustain such a mission over the decades it would require. These aren't just engineering problems. They're biological, medical, economic, political, and social problems. We'd need breakthroughs in multiple fields simultaneously. Life support systems that can recycle air and water with near-perfect efficiency for years. Artificial gravity, probably generated by rotating the spacecraft to create centrifugal force, which adds complexity and mass. Advanced medical capabilities to diagnose and treat injuries and illnesses far from Earth. Psychological support systems to maintain mental health during years of isolation. And propulsion technology significantly beyond what we have today. Some of these challenges might be solvable in the near term, within a couple decades. Others might require fundamental breakthroughs we can't predict. Artificial gravity on a crewed spacecraft, for example, likely requires a large rotating structure. Imagine a spacecraft shaped like a wheel or a pair of modules connected by a tether, spinning to create centrifugal force. The larger the radius, the more comfortable the artificial gravity. But larger structures are harder to build, harder to launch, harder to accelerate and decelerate. Radiation shielding might benefit from new materials. Researchers are investigating materials with high hydrogen content, advanced polymers, maybe even electromagnetic shields that deflect charged particles. Active shielding systems that create artificial magnetic fields around the spacecraft, mimicking Earth's magnetosphere. These concepts exist on paper and in small-scale tests, but scaling them up to protect an entire crewed spacecraft is a different challenge. Life support is solvable with existing technology, at least in principle. The ISS demonstrates that we can keep humans alive in space for months using regenerative systems that recycle air and water. Extending that to years requires better reliability, more redundancy, possibly closed-loop biological systems. Imagine growing plants on the spacecraft, not just for food, but for air recycling. Plants consume carbon dioxide and produce oxygen. They can also provide fresh food, which is psychologically valuable. But plants need light, water, nutrients, and care. They add mass and complexity. Some mission designs include small greenhouses, both for practical life support and for the psychological benefit of tending living things. Food is another challenge. Preserved food can last years if properly packaged and stored. Freeze-dried meals, vacuum-sealed, stored in controlled temperature environments. But variety suffers. After months or years eating the same limited menu, crew morale can decline. Fresh food would help, but producing it requires resources. Maybe you bring seeds and grow some fresh vegetables, lettuce, tomatoes, radishes, things that grow relatively quickly. It won't replace your entire diet, but it supplements preserved food and provides psychological benefit. Exercise is critical to maintain muscle and bone. Astronauts on the ISS exercise about 2 hours daily on resistance machines and treadmills to slow the loss of muscle and bone mass. Even with exercise, they still lose density, just not as fast. For a multi-year mission, you'd need robust exercise equipment, probably multiple machines for redundancy. If the treadmill breaks and you can't fix it, muscle and bone loss accelerates. By the time you reach Pluto, you might be too weak to function. Then there's the question of what you do with your time during the journey. You can't exercise and perform maintenance tasks 24 hours a day. You need downtime, rest, recreation. Entertainment becomes important. Movies, books, games, music. Communication with family and friends on Earth, despite the growing time delay. Hobbies, creative outlets, projects to work on. Some crew members might conduct research during the voyage, studying cosmic rays, the solar wind, magnetic fields, anything measurable from the spacecraft. Others might write, paint, learn new skills. Keeping the crew mentally engaged and psychologically healthy is as important as keeping them physically healthy. And there's the reality that things will go wrong. Equipment will fail. Systems will malfunction. People will get sick. You prepare for this as best you can. You bring spares for critical components. You cross-train crew members so multiple people can perform essential tasks. You design systems with redundancy, backup generators, backup computers, backup life support. You bring medical supplies, surgical tools in case emergency procedures are needed. You hope you never use them. NASA has extensive experience with long-duration missions, primarily from the ISS program. But the ISS is in low Earth orbit, a few hundred miles up. If something goes catastrophically wrong, the crew can return to Earth in a few hours using Soyuz capsules. On a mission to Pluto, there's no quick escape. The risk profile is entirely different. So would a crewed mission to Pluto ever happen? Maybe, but probably not in the next few decades. The technology gaps are too large, the costs too high, the risks too severe. Before we send humans to Pluto, we'd likely send humans to Mars first. Mars is much closer, about 140 million miles at closest approach, compared to Pluto's 3 billion. A Mars mission would take 6 to 9 months each way, not years. Mars has a thin atmosphere, but enough to provide some radiation shielding and potentially support local resource utilization. You could manufacture fuel, oxygen, and water from Martian resources, reducing what you need to bring from Earth. Mars is a more practical stepping stone. If we successfully establish a presence on Mars, demonstrate we can keep humans alive on another world for extended periods, then maybe we start thinking about more distant destinations. An asteroid, perhaps. Maybe the moons of Jupiter or Saturn, which are scientifically interesting and might have subsurface oceans. Europa, Enceladus, places where life might exist beneath ice shells. Pluto would be further down the list, a long-term goal for a mature, spacefaring civilization. Something we might attempt in the 22nd century if we're still expanding outward, if we've solved the technological and economic challenges, if we've developed infrastructure in the outer solar system. There's another possibility. Maybe humans never physically go to Pluto. Maybe we send robots so sophisticated, so capable, that they can do everything a human could do and more. Telepresence systems where human operators on Earth or on Mars control robotic avatars on Pluto in near real time, using advanced prediction algorithms to compensate for light speed delay. Or autonomous AI systems that can explore and make decisions without human input, conducting science as effectively as trained researchers. If we can achieve that level of robotic capability, the case for sending humans weakens. But there's something compelling about humans going in person. Something fundamental about direct experience, about standing on an alien world and seeing it with your own eyes. Not through a camera feed, not in a virtual reality simulation, but actually being there. That direct connection to the cosmos, that physical presence in places no human has ever been. It's not rational. It doesn't make economic sense. But it speaks to something deep in human nature, the drive to explore, to push boundaries, to see what's beyond the horizon. Pluto represents the frontier of our solar system, the boundary between the planetary region and the Kuiper Belt, the vast swarm of icy bodies beyond Neptune. It's a world we barely understand, glimpsed only briefly by a single flyby probe. There's so much we don't know. What's the interior structure? Is there really a subsurface ocean? What's the geology of regions New Horizons didn't photograph? How does the atmosphere change over Pluto's long year? What are the surface compositions in detail? Some of these questions could be answered by orbiter missions or landers, robotic missions that stay at Pluto for extended periods. NASA has proposed such missions, but they're expensive and compete with other priorities. A Pluto orbiter would take a decade or more to arrive and would cost billions. In the current budget environment, it's hard to justify. But eventually, maybe we'll go. Maybe in a century or two, when space travel is cheaper and faster, when we have fusion drives or antimatter propulsion or some technology we can't imagine yet, when the trip to Pluto takes months instead of years, when radiation shielding is routine and artificial gravity is standard, when we have settlements on Mars and the moons of Jupiter and infrastructure throughout the inner solar system. When that day comes, Pluto will still be there, waiting. Its icy plains and towering mountains, its nitrogen glaciers and methane dunes. Its enormous moon, Charon, hanging motionless in the sky. Its position at the edge of the planetary system, gateway to the Kuiper Belt, and the true deep outer solar system beyond. Until then, we have the data from New Horizons. Images of a world far more complex and beautiful than anyone expected. Heart-shaped Tombaugh Regio with its smooth nitrogen ice plains. Norgay Montes and Hillary Montes, mountain ranges 2 to 2.2 miles high, made of water ice. Bladed terrain. Strange formations where methane ice has eroded into sharp ridges. Evidence of cryovolcanism, ice volcanoes that erupt liquid water or ammonia instead of molten rock. A hazy atmosphere with layers of photochemical smog. Pluto is not the dead frozen rock people imagined. It's an active, dynamic world, with geology driven by processes we're still trying to understand. It's a world that deserves further exploration. And the question isn't really whether humans will ever reach Pluto. The question is when and how and why. What will drive us to make that journey despite the challenges? Scientific curiosity? The desire to expand humanity's reach? Economic incentives we can't foresee? Political competition between nations or blocs? Some combination of all these factors. History suggests that exploration happens when multiple factors align. Technology becomes available. Economic conditions make it affordable. Political will provide support. Cultural values celebrate it. All of these have to come together, and they rarely do. The Apollo program happened because of Cold War competition between the United States and Soviet Union, because economic prosperity in the 1960s made it affordable, because technology had advanced to the point where it was just barely possible, and because American culture at the time valued bold technological achievement. Remove any one of those factors, and Apollo likely doesn't happen. For a Pluto mission, we'd need a similar convergence. We don't have it now. We might never have it. Or we might find it decades or centuries from now, under circumstances we can't predict. What we do have is the knowledge that it's possible in principle. The laws of physics don't forbid it. The distances are vast, but not infinite. The challenges are severe, but not insurmountable. With enough resources, enough time, enough will, we could do it. We could send humans to Pluto. The journey would take years, 5 or 7 or maybe 3 with advanced technology. The crew would endure radiation, isolation, confinement, and the constant risk that any system failure could be fatal. They'd arrive at a frozen world where the sun is just a bright star and the temperature is hundreds of degrees below zero. They'd explore, conduct research, and either return home after an equally long journey or remain as permanent residents of the outer solar system. It's a daunting vision, difficult to the point of seeming impossible. But so was landing on the moon before we did it. So was reaching Pluto with a robotic probe before New Horizons. Human capability expands when we push against limits. Maybe someday, someone will stand on Pluto's surface and look up at Charon filling the sky. They'll see Earth as a pale blue dot next to the sun, barely visible, a reminder of home 3.5 billion miles away. They'll know they're farther from home than any human has ever been. They'll feel the cold seeping through their suit despite the heaters, the low gravity making every movement strange. And they'll look around at the alien landscape, the nitrogen ice plains and water ice mountains, the methane dunes and hazy sky. They'll be the first to see it with human eyes. That moment, if it ever comes, will justify the journey, not in economic terms, not in any rational calculation of cost versus benefit, but in the simple fact of being there, of extending human presence to the edge of the solar system, of proving that distance, however vast, cannot contain us forever. How long would it take to reach Pluto? Years. Multiple years of your life, spent in a metal tube crossing the void. Is it worth it? That depends on what you value. If you value comfort, safety, and the familiar, then no, it's not worth it. Stay on Earth, where the air is breathable, and the gravity is comfortable, and help is always nearby. But if you value exploration, discovery, and pushing boundaries, if you want to see things no one has seen and go where no one has gone, then maybe it is. Maybe the years in transit are the price of admission to the most exclusive club in existence, the handful of people who've left Earth behind and traveled to another world. Not many people would choose to make that journey, given the option. Most would decline, and reasonably so. But a few would say yes. A few would volunteer, knowing the risks, knowing the hardships, knowing they might not return. Those few are the ones who'll take us to Pluto when the time comes. Until then, Pluto remains what it's been for most of human history. A distant point of light at the edge of the solar system. A challenge waiting for future generations. A reminder that the universe is vast beyond comprehension and that we've only just begun to explore it. The journey to Pluto is measured not just in miles or years, but in the development of technology, the accumulation of knowledge, and the evolution of human capability. Every advance in propulsion brings us closer. Every improvement in life support makes the journey more feasible. Every mission to Mars, or the asteroids, or the moons of Jupiter teaches us lessons we'll need for Pluto. We're building toward it, even if we're not consciously aiming at it. Each step outward prepares us for the next. And eventually, the step to Pluto will become possible, then practical, then routine. How long will that take? Decades, certainly. Probably a century or more. Maybe longer, depending on how history unfolds, what priorities we set, what challenges we face. But it will happen. Humans have always explored. We crossed oceans in wooden boats when we barely understood navigation. We climbed mountains that killed most who tried. We ventured into deserts and ice fields and jungles where survival was uncertain. We've always pushed against the limits of the possible. Space is the ultimate frontier, the final ocean to cross. And Pluto, distant and cold and strange, is one of the far shores waiting for us. The journey begins with understanding what it would take. Years of travel through radiation, soaked, vacuum, isolation from everything familiar, dependence on machines and the skill of your crew. The knowledge that rescue won't come if things go wrong. It continues with developing the technology to make it survivable. Propulsion systems that cut travel time. Radiation shielding that protects fragile human biology. Life support that functions flawlessly for years. Artificial gravity to prevent the long-term effects of weightlessness. And it culminates with the decision to actually go, to commit resources, to accept risks, to send people on a journey measured in years to a destination 3.5 billion miles from home. That decision hasn't been made yet. It won't be made for a long time. But when it is, when the ships finally launch and the crews begin their long journey outward, they'll be continuing a story that started when the first humans looked up at the night sky and wondered what was out there. They'll be answering a question that's driven us for millennia. What lies beyond the horizon? What's at the edge of the known world? Can we reach it? For Pluto, the answer is yes. We can reach it. It will take years. It will cost enormously. It will risk lives. But we can do it. And knowing that changes everything, because it means the solar system, vast as it is not beyond our grasp. The outer planets, the Kuiper Belt, even the distant Oort cloud, these aren't unreachable. They're just far. And distance, however intimidating, is just a number. A challenge to overcome, not an absolute barrier. That's the real answer to the question. How long would it take to reach Pluto? Long enough to test everything we are. Long enough to force us to develop new capabilities. Long enough to be a genuine achievement when we finally do it. But not so long that it's impossible. That's the sweet spot where exploration happens. Hard enough to matter, possible enough to attempt. Pluto sits right in that zone, waiting for the generation that decides to try.